All right, welcome everyone to today's TCS Plus talk. My name is Gautam Kamath and I'll be the host for today. Just letting you know about some of the upcoming talks on our schedule. 1 week from today, we have Rahul Ilango. 2 weeks from today, we have Michael Kim. And 3 weeks from today, we have Cliff Stein. This might be the end of, that might be the final talk of the season. We're still deciding, but it's been exciting so far. And thank you all for joining us on this very interesting journey through this term. But anyway, as for today's talk, today we're very lucky to have Mark Bunn as our speaker. Mark is an assistant professor at Boston University. Before this, he was a research fellow at the Simons Institute for the Theory of Computing. And before that, he was a postdoc at Princeton University. He did his PhD at Harvard University before all that. His interests are in differential privacy, naturally, which a lot of you are here for, but he also does a lot of work on lower bounds, including, say, real polynomial approximation as well. He's the winner of a Best Paper Award at iCalp. And without further ado, I'm going to pass it off to Mark. Feel free to share your screen now.
Okay. The host has disabled screen sharing. I see I've been removed as co-host.
Oh, let me see if I can make you co-host. You are now co-host. I think, is that the right one? There's two of you here. Or more, make co-host.
Try the other one, please.
You are now all co-host.
Looks like as a result of this.
There you go.
All right, there we go.
Perfect.
Okay, sorry everyone for the hiccup. So thank you to Gautam, Clement, and Nindya and all the other organizers for the invitation to speak today. I'm really happy to tell you about this work, which is joint with Roy Livni and Shai Moran about an equivalence between differentially private classification and online prediction. So yes, a lot of us are getting used to this new format of online talks, and I've discovered that my debilitating need for validation means that I have an easier time when folks are able to turn on their videos and smile and nod along as much as possible. So it's much appreciated if you can do that as much as you're comfortable. All right, so, and again, as Gautam said, of course, feel free to stop me and interrupt with questions or comments as we go along. Okay, so this talk we're going to work with a model of differentially private classification. So that's the general framework we're working with as follows. You have a bunch of points which are labeled either positively or negatively according to some unknown classification rule. And what we'd like to do is we'd like to learn a new classification rule which approximately labels not only these points, but also fresh draws from the underlying distribution. And we'd like to do so in such a way that we protect the privacy of the example. So we can imagine that these samples are consisting of sensitive personal data. We'd like to be able to learn a classification rule that's not only accurate at separating these red points from green points, but protects the privacy of the individual samples. So we're going to be working more or less in the usual model of pack learning. Introduced to the computer science community by Valiant in 1984. So in this model, what's known to us is a space of examples X, a so-called concept class, which consists of Boolean functions over the space X. And what's unknown is going to be a distribution D over the space of examples X, as well as some unknown target concept C, which we're trying to learn. Okay, so pictorially, what we have here is this unknown distribution D over X. We get a sequence of IID labeled samples. So IID examples X1 through Xn from X, which are labeled according to this unknown concept C. And our goal is to feed the sample S into a learner L and produce a hypothesis H, which is itself a Boolean function over X. And hopefully this hypothesis that we learn will closely approximate C, at least with respect to the distribution D. So to be more formal about this, we say that L is an alpha beta pack learner for two positive parameters, alpha and beta. If for all underlying distributions D and for all possible choices of the true classifier C, we're very likely to learn a hypothesis with good error. So here, good error means that with probability at most alpha over a fresh draw from the distribution D, H is not going to not going to disagree with C. Okay, and this property of H having low error with respect to C on the distribution D should happen with probability at least 1 minus beta over the random choice of the sample S from D and any internal coin tosses of the learning algorithm L. Okay. So just to make everything a little bit more concrete, we can turn to one of my favorite examples and one that's been like a thorn in my side for something like 5 years, which is this problem of just learning one-dimensional threshold functions. Okay, so this is something that we can do really easily in the non-private pack model. So here, the space of examples X is just going to be, say, the natural numbers between 1 and t. The concept class is going to consist of all threshold functions, f sub t, which are 1 if they're given a point which is at most some parameter t, and 0 if x is bigger than t. Okay, so this is f sub t for every t and t. Okay, so how would we learn a threshold function? So suppose our examples are coming from this distribution drawn in blue here. Okay, and suppose we get a sequence of labeled samples according to this threshold function here. So for everything smaller than this blue line, we're getting a positive example, and for everything bigger than this blue line, we're getting a negative example. Okay, so what would be a natural, classification rule which labels these samples? Well, one thing we could do is we could create a threshold function which thresholds at the largest positive example. Okay. So we look at our sample, we look for the largest positive example and say, well, our hypothesis is just going to be 1 up to that point and then switch to 0 afterward. Okay, so a fact you can show is that as long as the number of samples you're given is at least something like log 1 over beta over alpha, then with probability at least 1 minus beta over the random choice of the sample, we're going to, this purple thing that we've learned is going to be a good classification rule. Okay, so it's going to agree with the target concept up to error at most alpha with respect to the distribution. All right, something has happened. Screen. Okay. All right. So this problem of learning thresholds is just one example. For the rest of this talk, so I don't have to carry these parameters alpha and beta around all over the place, I'm just going to fix them to be, say, 1%. So we're going to be aiming to learn hypotheses that are good up to 1% error and with confidence at least 99%. So with those fixings of everything to constants in mind, this problem of learning thresholds we've seen to be possible as long as the number of samples that we have is some constant, which is independent of the domain size t. Okay. So in general, the sample complexity of pack learning an arbitrary concept class C is known to be characterized by a combinatorial property of the class C, which is known as its VC dimension after Vapnik and Turbanenkis. Okay, so this VC dimension, which I'm not going to explain to you in any detail, is just a combinatorial measure of the complexity of the class C. It's always going to be at most log of the size of C in the case where C is finite, but it can be much smaller. So in the case of threshold functions over a domain size T, it's much smaller than log T. It's always going to be 1 actually, independent of T. So what this means is that thresholds are learnable with sample complexity independent of t. And in fact, they're learnable even if t is infinite. Okay, so we can learn, threshold functions over the natural numbers or over the real numbers, whatever you like, in a totally ordered domain with constant sample complexity. Okay, so that's non-private classification. Now, we're going to be interested in this work in differentially private classification, where we augment the PAC model by popping differential privacy on top. So what we're going to additionally demand from our PAC learners is that they satisfy what's known as epsilon delta differential privacy. What does this mean? So we're going to demand that this learning algorithm L is differentially private, meaning if I look at any pair of samples, labeled samples x1, c of x1, et cetera, through xn, c of xn, differing in one row, the distribution over hypotheses that I get by running the learner on sample S should be statistically close to the distribution I get by running the learner on sample S prime. Okay. So that means that just by looking at the hypothesis that you produce by the learning algorithm, you shouldn't be able to tell whether the person whose data was used in the row on which these two differ was in the data set or not. Okay. So differential privacy quantifies this notion of closeness using two positive real parameters, epsilon and delta. So we say that L is epsilon delta differentially private if for all pairs of neighboring data sets S and S prime, and all sets of outcomes that could be produced by the learner, the probability of landing in that set when the data set is S is at most the multiplicative e to the epsilon times that probability when the underlying data set is S prime, plus an additive delta. Okay, so this is just one way of saying that the distributions of L of S and L of S prime are close. It's not terribly important what the definition is for understanding the talk, but it is important for the results to be correct and interesting. Okay, so any questions about this? So one point that I want to make about this definition of epsilon delta differentially private PAC learning is that this condition of epsilon delta differential privacy should hold in the worst case over the. So it should hold for all pairs of data sets S and S prime, even ones which are not correctly generated as IID samples from some underlying distribution and labeled by some concept in the class C. Okay, it just has to be any pair of data sets that have the right syntactic structure. Whereas the notion of PAC learning is an average case notion. We just require that the learner output a good hypothesis when the data is actually generated IID from some distribution.
So just to clarify, say even if a data set comes up that has probability 0, you still want to be private on that.
Sorry, I didn't hear part of that, but even if a data set,
if a data set is say very, very, very unlikely, say probability 0 or 0.1, you want it to still be private even on this, right?
For sure. Probability 0, I guess there's a question of whether that data set is, syntactically restricted from ever appearing versus, it depends on what you know about the distribution D, I guess. If you're allowed to make some assumptions on the distribution D, that such data sets, that some kind of data set would never appear, then you could pre-process your data set to actually ensure that this never appears. And
sure, if you're trying to sample a number from 1 to T, but you get an elephant instead, then that's not kosher, let's say.
Yeah, exactly. Then that's something that you can deal with. Anything else? All right, so what do we know about differentially, So why should we care about private learning in the first place? So taking even a step back, why should we care about differential privacy in the first place? So, by now it's pretty well understood that differential privacy is a really fantastic notion for understanding privacy for statistical data analysis. And one really nice property is that you can prove mathematically is that it's provably resistant to all known privacy attacks that an adversary looking at the outcome of a private data analysis could lodge. And moreover, it's resistant to all unforeseen possible future attacks. So this gets us out of this cat and mouse game where somebody comes up with a privacy definition, somebody else comes along and breaks it, and so on and so forth. Second, some of these properties that make it robust to attacks are also useful in doing mathematical analysis that we love to do as theoretical computer scientists. So in particular, differential privacy is robust to post-processing, meaning I can look at the outcome of a differentially private algorithm and then do whatever I want to it, as long as I don't touch the data set again. And the resulting algorithm will still be differentially private. And moreover, it degrades, differential privacy degrades gracefully and predictably under composition. So I can build more complex algorithms out of simpler differentially private parts and get guarantees about how private the resulting algorithm is as a whole. So why study differentially private PAC learning in particular? Well, one more practical motivation is that it's a useful abstraction for a lot of the kinds of statistical analyses that one would like to carry out on sensitive data. But it's interesting, I think, for what I would say are deeper scientific reasons. So it's really very closely connected to other fundamental notions of learning and issues of generalization that are pervasive, not only in theoretical computer science, but in the empirical sciences in general. So a variant of differentially private learning called learning in the local model of differential privacy is known to be equivalent in some sense to statistical query learning. And moreover, so differential privacy can be thought of as a notion of algorithmic stability. So differential privacy says, whatever a learning algorithm does should not be too sensitive to small changes in the input. So this is a notion of stability. And stability is very intimately tied to generalization of learning algorithms. And in particular, a fairly recent line of work has shown that differential privacy is an extremely powerful tool for ensuring generalization in interactive settings. So for solving this problem of preventing false discovery in interactive data analysis. Okay, so I want to quickly revisit this example of learning one-dimensional thresholds to illustrate why differentially private learning is also a technical challenge. So if we go back to this learning rule that we had for one-dimensional thresholds, where we just picked the threshold at the largest positive example, this is good statistically, but it's super non-private. So this learning rule reveals one example in the clear. So it very much does not protect the privacy of the training examples. Okay. And in fact, coming up with any differentially private learner, at least from first principles, is not totally obvious. And nailing down the sample complexity turns out to be a surprisingly interesting question. So let's talk for a bit about, at least generically, about the problem of determining the sample complexity of private learners. So unless otherwise stated, I'm going to, again, make my life easier by suppressing parameters and setting epsilon to be a small constant, say 0.1, and delta being 1/10n. So don't worry too much about these if you question my choices for the parameters. But think of these as sort of like the most permissive choices of parameters, the ones which are most interesting for studying lower bounds in particular. So this this work of Kasi Viswanathan, Lee, Nassim, Raswadnikova, and Smith, which introduced the model of differentially private pack learning, actually introduced the generic learner, which showed that for any finite concept class C, there's a differentially private pack learner for that concept class, which uses something like order log. Okay. So remember that in the non-private setting, the non-private sample complexity of learning a class was its VC dimension, which is always at most log size of C, but could be much smaller. So this is some good progress, but doesn't always take us down to the VC dimension, which we know is achievable in a non-private setting. So there's been a fair amount of work. This is a totally non-exhaustive list, just something that I put together last night of specific concept classes for which people have developed improved learners with improved sample complexity guarantees for specific concept classes of interest. I believe we had a comment in the chat.
No, I was just commenting on the choice of delta to be 1/10n. I mean, it might seem small, but just to be clear, that's actually like normal to look at that range of delta, right? Because delta greater than 1/n is not interesting at all.
Yeah, so looking at delta being bigger than 1/n is uninteresting because you could just sample, say, something like a 1/n fraction of your data set and then run a non-private learner on that. So that's uninteresting technically. It's also uninteresting for privacy because it doesn't seem like a good idea to sample a random person in the data set and expose their data in the clear. So we do think of this as like the most permissive setting of delta. Anything else?
Just a question, Mark, about the generic learner. Does it only apply in the pack setting or does it also work for the agnostic setting?
Good. So this also works in the agnostic setting. Yep. So in order to get sample complexity, something like log C, you don't even need to assume that the data is that the data set is realizable. So it doesn't need to be labeled by some function in the concept class, and you're going to do just as well, or approximately just as well as the best function in the concept class that that would label your distribution. Okay, great. Okay, so as I alluded to, in the setting of differential privacy, it turns out that even the simple problem of learning one-dimensional thresholds turns out to be surprisingly interesting. So it's known that the sample complexity of privately learning thresholds is something like the log star of the domain size t, okay, where log star is the iterated logarithm, so the number of times that I have to take the log of t in order to get down to 1. So this is some like extremely slow growing function of t. If t is like the number of atoms in the universe, this is something like 6. But nevertheless, it's some function which grows with t. So what this pair of results characterizing the sample complexity of privately learning thresholds shows, in particular, is that unlike in the non-private setting, privately learning thresholds is impossible over infinite domains. So you just can't do it over the natural numbers or the real numbers. Okay, so the natural question that results like this raise, we know now that the VC dimension, which was 1 for thresholds, can't be a characterization of the sample complexity of private learning. So can we come up with a combinatorial characterization of of the sample complexity of privately learning a concept class C? And I wish I could say that we solved this problem in this work, but we don't. So we set our sights a little bit lower. At least what we do in this work is we try to address the question of when can an infinite class C, for instance, threshold functions over the real line, or something simpler, for instance, point functions over the real line. When can we characterize when an infinite class C is privately learnable using a finite number of samples? Okay.
Mark,
So,
there's 2 questions.
Yep.
One question is log 1 over delta should appear in the sample complexity, right, which might be larger than log star of t.
Yeah, that's right. So the dependence on delta, if you aren't suppressing it, is going to be log 1 over delta, I believe, in both the upper and lower bounds.
Cool. And there's another question asking
Dominating
about
factor.
what is learning polygons?
Oh, so these are learning polygonal shapes in the plane. So this is like a convex hull of points. So your function is the indicator of the convex hull of a collection of points in the plane. And I think in this work, they also address like unions of polygons and intersections of polygons. This is in reference to this example here. Okay, anything else? All right, so this is what we prove in this work. So let's let C be an arbitrary concept class with what's known as the Littlestone dimension, the Littlestone dimension D being L of C. Then the sample complexity of privately learning the class C is sandwiched between log star of D, the Littlestone dimension, and what we show in this work is that it's at most 2 to the order D. Okay, so up to enormous factors, the sample complexity of privately learning a class C is characterized by this parameter called its Littlestone dimension. And actually, so it's important for me to point out that the lower bound actually follows from this prior work of Alon, Livni, Maliaras, and Morin from last year, who showed that, as I mentioned on the previous slide, that learning thresholds require sample complexity log star of D. And the reason why this works for general classes is one can show that associated to every class with large Littlestone dimension, one can actually find a copy of one-dimensional thresholds embedded in it. So there's a sense in which one-dimensional thresholds are kind of complete for classes with large Littlestone dimension. And they left as an open question in their work, proving the converse characterization, which is what we do. Okay. And again, the higher order bit of this characterization is that a concept class C is differentially private learner with some finite number of samples, if and only if it has a finite Littlestone dimension. Okay, so I haven't told you at all what Littlestone dimension is, and I'm going to devote the next few slides to describing that.
Just before that, Mark, does VC dimension have any known characterization like this one?
So do you mean,
like
so what do you mean by like this one?
Like threshold, like connection to some basic hard instance.
Oh, that's a great question. Not to my knowledge. Maybe somebody else would know. I think there may be some sense in which all functions on a hypercube are complete for VC dimension just by identifying the shattering set of your class and looking at all functions on that. So I think in some sense that's similar. I don't know. I would need to think about it a little bit more to match them up to ensure that it's that correspondence is exactly correct. But that's the closest approximation I have. Yeah, I guess all functions on a set of size D would be the analog.
So is it fair to think of this Littlestone dimension to capture the complexity, the sample complexity of private learners, like similar concepts as we have for non-private setting as VC dimension? Is it right Is it the right way to think about it?
So it's probably not right to think of Littlestone dimension as capturing the sample complexity. So actually the best, I'll pose this as an open question at the end, but the dream theorem, the best one could prove just using Littlestone dimension. Sample complexity is between log star and D itself, okay? So the reason for that this is the best possible upper bound is that there are classes that have, you know, maximal VC dimension and maximal Littlestone dimension being log of the concept class size. So even, you know, for these classes, non-privately learning them requires omega D samples. So this is the best characterization one could get just in terms of Littlestone dimension itself. And, you know, another open question would be to find a different parameter which actually nails down the sample complexity in a tight way, like VC dimension does for the non-private case. All right. Okay, so again, I wanted to spend the next couple of slides talking about the Littlestone dimension. And as foreshadowed by the title of the talk, Littlestone dimension comes up in a different setting of learning, in the online learning setting. Now, I know that many of us are by now thoroughly familiar with online learning, but it's, of course, worth going over concretely what model we care about is. So in order to describe the Littlestone dimension, we're going to be talking about what's known as the online mistake bound model, which is due to Littlestone from 1988. So in some respects, the setup is similar to the PAC model. So what's known to everybody is a space of examples X and a concept class which we're using to label examples in X. And what's unknown is a specific target concept, little c, which we're using to label the data. The difference with the classification setting is that there's no notion of statistics. Nothing is statistical, so no distribution. Okay, so everything in this online learning model is going to be deterministic, worst case. Okay, so in this model, we're going to envision a two-player game between an online learner and an adversary. So in the first round, the adversary is going to pick a sample, pick an example X1 and X. And the online learner is going to try to predict what the concept should do on the sample. So what we're actually going to do for technical reasons to make stating things later in the talk easier, let's have the online learner report an entire hypothesis that it's guessing for how all examples should be labeled. Okay. And then once the adversary sees what the online learner picked, it's going to report the true label of X1. Okay, so give it feedback on how well it's done. Okay, and then this game is going to proceed in rounds like this. So in each round, the adversary is going to pick another example. The learner is going to choose a new hypothesis, and the adversary is going to tell it whether it was right. Okay, and this is going to proceed indefinitely. Okay, so this game is going to run until the end of all time. Okay, so we're going to say that a learner makes a mistake in round I if its prediction disagrees with the true label on the example that it was given. Okay, so if C of Xi is different than HI of Xi. And we're going to say that a learner L learns the concept class C with mistake bound D. And for every possible target concept and every adversarial strategy, the learner is guaranteed to make at most D mistakes. So even though they're playing this infinite game, and in principle, the learner could be messing up on every other example, what we want to guarantee is that after a finite number of mistakes, D, the learner will be guaranteed to never make a mistake ever again, regardless of whatever the adversarial strategy is.
There's a question. So we pay when the hypothesis is wrong only on the specific point of interest in this round?
That's right. A mistake is only judged relative to the example that we were given in this round. It can disagree arbitrarily on every other point. So if you've seen this model before, what you've likely seen is instead of having the online learner report a full hypothesis in every round, it just outputs a prediction on xi. It's going to be equivalent for us to look at this slightly more elaborate model, but it's useful for stating things later on to have the online learner report a full hypothesis. Okay, great. So again, it's helpful to look at this example of learning one-dimensional threshold functions.
Question, is the online learner proper? Does it have to, I guess, suggest hypotheses within the concept class?
Good. So nothing I'm talking about today is proper. So the online learner in this case is not going to necessarily have to be responding with a hypothesis HI that's in the concept class C. It can be an arbitrary hypothesis.
Also, does the so when we were talking about mistake, is the mistake at point xi, right? So that the class H2 can be completely wrong about x1, is that right?
Good. So yeah, H2 could be completely wrong about x1. It's probably not going to be helpful for the learner to be doing that. But I guess the way that the model is stated, H2 could disagree with.
That doesn't count as a mistake.
Right, that wouldn't count as a mistake. Okay, so again, it's helpful to be a bit more concrete. So let's look at an example run of a reasonable algorithm for online learning threshold functions based on binary search. So in this example, okay, so in the first round, the adversary is going to select an example. Let's say this one over here, unlabeled. And the next step is for the learner to make a hypothesis, in particular, including a label for this example. So the online learner doesn't know anything at this point, so it might as well guess, the least informed kind of hypothesis, which is a threshold at the middle of the data domain. In particular, its guess for the label of this example is going to be positive. Okay, so in the next step, the adversary is going to reveal the true label and say, yep, you did a good job. You labeled this one correctly. Okay, so in the next round, the adversary is going to again select another example. Here, again, the hypothesis that the learner has is going to say that it should be positive. But let's say, oh no, the adversary reveals that the true label should have been negative. Okay, so what's going to happen here is the learner is going to update the hypothesis that it has in its head using binary search. Okay, so it's now going to say, everything to the left of this modified threshold is positive and everything to the right is negative. Okay, so it's going to get another example. In its head, it's going to say it's negative, but then the adversary might reveal that this was positive. So again, it's going to keep doing binary search. Okay, so why does this work? So if we look at the space of threshold functions, so this is, not all online learners have to be proper, but this one turns out to be. So every time the learner makes a mistake, the set of threshold functions which are consistent with the data seen so far gets halved, okay? So if our domain size is t, the learner can make a total of log t mistakes before it's, nailed down the concept. All right, so we're going to define for an arbitrary concept class, its Littlestone dimension, to be the least value of d, for which there exists an online mistake-bounded learner for C with mistake-bound D. So what we saw on the previous slide was that the class of threshold functions over domain size T has a online mistake-bounded learner with mistake-bound log T. So we've shown the upper bound that little stone dimension of thresholds on domain size t is at most log t. And this turns out to be tight. So a general fact about online learning, which I want to point out, is that there's sort of one canonical algorithm to rule them all. So if I give you a concept class C with little stone dimension D, it turns out that there's one canonical algorithm. You can think of this as running some souped up version of binary search. The details of the algorithm aren't so important, which is always going to achieve this mistake bound. Okay, so there's one specific algorithm that has a mistake bound L of C for every concept class C with finite little stone dimension. All right, so again, now that we have the definition of little stone dimension, we can restate the main result a little bit more carefully. So what we show is that if we have a concept class C with some finite little stone dimension D, then there exists a differentially private pack learner for that concept class using something like 2 to the D samples. Okay, so with the remaining 20 minutes or so, I want to talk about some of the ideas that go into the proof of this result. So at a high level, the way that we prove this result is using 2 phases. So in the first phase is going to have nothing to do with privacy at all. So what we're going to do in this first phase is we're going to show that if that any concept class with finite little stone dimension, and in particular an online mistake bounded learner, there's going to be a pack learner for that class, so in the statistical classification setting, which satisfies a special new property, yet another thing I have to define, called global stability. Okay, so what this global stability property is that we're going to have a learner for C, which is reasonably likely to output some particular hypothesis H, meaning for every distribution D and every target concept in the class C, there's going to be some hypothesis H, possibly depending on D and C, which the learner is likely to output when run on a random sample S. Okay, and here by likely, I mean with probability exponentially small in D. Okay, so in some ways, this is an analog of various stability notions that have been considered in the literature, but in other ways it's different. So often, stability notions in the literature will talk about an algorithm's distribution not changing too much when I change one sample. But this notion of global stability says I can change the entire sample and the distribution won't change too much, in the sense that there will still be some hypothesis which is likely to output. Okay, as long as the sample that I change to is again an IID draw from the same distribution labeled by the same concept. Okay, so phase 2 is then to show generically that any globally stable pack learner satisfying these conditions, as in lemma 1, can be transformed into a differentially private pack learner. So is the setup for how we plan to prove this clear? All right, so let me try to tell you some of the ideas that go into this conversion from online learning to globally stable learning. Again, this is just going to be the proof idea. The actual proof has to deal with a number of other issues, which I'm going to sweep under the rug. So, so here's the idea. So we're going to just, write down everything that we know. So we're going to be working in the pack learning setting. So we have some distribution D and some target concept C. And what we have at our disposal is the fact that this concept class C is online learnable. So there's going to be a mistake bound of D for it. And in particular, this algorithm, the standard optimal algorithm, which learns it using mistake bound D. Okay, so in the pack setting, we're given as input a sample, which consists of labeled pairs x1, l1 through x and ln. And with all this stuff at this disposal, what are we going to do? Well, we're going to do the only thing we can do, which is run the standard optimal algorithm on the sample, as if the sample were what the adversary and the online mistake bound model were giving us. Okay. So this has a name. It's considered already in the literature, online to batch conversion. Okay, so I want to draw your attention to a number of cases that we could consider when trying to analyze what happens when we run the SOA on the sequence of samples. So the first case I want to identify is what we'll call case D, which is that with reasonable probability over the choice of the sample S, the standard optimal algorithm is going to make exactly D mistakes. All right, so that's case D. Case D minus 1 is going to be the same thing, except we're going to look at the probability that it makes exactly D minus 1 mistakes, and so on and so forth. Okay, so by an averaging argument, at least one of these cases has to happen, right? So these exhaust the probability space, and each one, the criterion for each one is that it happens with probability at least 1 over D plus 1. So at least one of these happens. So what we can do is we can just, randomly guess a case, okay? And as long as we guess correctly and something good happens in that case, this probability of 1 over D plus 1 that we guess correctly can just be absorbed into this, exponentially small n D. So now let's analyze each of the cases separately. So case D is easy for us to handle. So this is, again, the probability that the SOA run on D makes exactly D mistakes is at least 1 over D plus 1. So what I'm going to claim in this case is that the probability that the SOA literally outputs the true target concept C is going to be at least 1 over D plus 1. All right. So why is this the case? So if the SOA makes exactly D mistakes on some sequence, the claim is that it must have actually found the target. Okay, so why is that? So if not, then in the next round, the adversary could find some point on which the concept that the SOA identified disagreed with the true target, and it would force the SOA to make an additional mistake. All right, but because the SOA was mistake bounded using by D mistakes, this can't be the case. Okay, so this one was easy. So the SOA literally outputs C with reasonable probability. Now what happens in case D minus 1? All right, so in this case, we're looking at state of the world where the probability that the SOA makes exactly D minus 1 mistakes is at least 1 over D plus 1. But now we're sort of in trouble. So D minus 1 mistakes is no longer enough to pin down the target concept, okay? Because the SOA still has the flexibility to make an additional mistake. So here's what we're going to do instead. We're going to consider what happens, not when we run the SOA on one sample, but what happens when we run the SOA on 2 fresh samples, call them S1 and S2. All right, so if we're in the setting where the probability that the SOA makes exactly D minus 1 mistakes is large, then still with reasonable probability, at least 1 over D plus 1 squared, the SOA is going to make exactly D minus 1 mistakes on both of these fresh samples. All right, so let's see what happens. We can now decompose into 2 subcases. So the first subcase is a good one for us. So in this subcase, H1 is equal to H2 on every example with high probability. So this is a good case for us. So if the collision probability is high, then that means that the probability associated to any particular hypothesis, so some particular hypothesis has to be high, which means we can just output, the output of the SOA, and that's going to be good for us. So the remaining case that we have to deal with is where with reasonable probability, H1 is different from H2. So in this case, we can brute force to find some point on which H1 is going to disagree with H2. Okay, and then using this point, do something. So what we're going to do here is we're going to define two new hypotheses, H1 prime and H2 prime, that we get by augmenting the samples S1 and S2 to force the SOA to make an additional mistake. So what we're going to do here is we're going to augment S1 with X labeled by H2 so that we force the SOA to make a mistake here. And we're going to augment S2 by X labeled by H1, again, to force the SOA to make a mistake here. So for each of these hypotheses, H1 prime and H2 prime, the SOA makes exactly D mistakes. All right. So the claim now is that if we're in this subcase, one of these has to be the target C. Now, why is that? So if H1 agreed with C on X, okay, then that means H2 prime is going to have been fed a sequence of examples which is totally consistent with the target concept C, and it made D mistakes. So that means by the previous reasoning that it must have nailed down the target concept C. Similarly, if H2 of X were equal to C of X, then H1 prime would have made exactly D mistakes when run on this sequence of samples, and they're entirely consistent with labeled data according to the true concept C. So this must be equal to C. All right, so those are the only two possibilities. So one of these has to be, in fact, the target concept C. So what we get at the end of the day is that it's totally fine for us to just output each of these H1 prime or H2 prime with probability half. So that's going to guarantee us that we produce C with total probability at least something like half times 1 over D plus 1 squared, which is definitely bigger than 2 to the minus order D. Any questions about this?
Sorry if this is too trivial, but could you explain the subcase A again?
Yeah. Okay, so in subcase A, what we're saying is that if we run the standard optimal algorithm on 2 fresh samples with high probability, say at least 99 over 100, we're going to get literally the same hypothesis. Okay, so the collision probability, the probability that I'm getting the same hypothesis when running the SOA on fresh samples is high. So you can work out that this implies that the probability that I output some particular hypothesis, that there exists some hypothesis, such that the probability that I output that particular hypothesis also has to be high. So that means if I just run the SOA on one sample and then output that the hypothesis that I get there, this hypothesis that I'm producing is one that's frequently appearing under SOA run on some labeled sample.
Thank you.
Anything else?
So in the global stability definition, you said there will be some H which will be output with the, but here you are actually going after the target.
Yeah, so there's a distinction between these subcases. So in subcase B, we are literally going after the target. In subcase A, these H1 and H2 could be different things. They could be things that you get by making strictly smaller than D mistakes. So it's not always going to be the case that you're going to output C with high probability or with noticeable probability. You could have ended up in the subcase A, which would give you something else. Okay, So if there are no more questions, let me kind of wrap up this part of the proof at least. So case D, we dealt with. The probability that we output the true target concept was reasonably high. Case D minus 1, the probability that we output some hypothesis H, be it the true concept or something else, is reasonably high. And using an inductive argument, you can show something similar for each case D minus K. So your algorithm now is not going to have to just make 2 pairs of samples fight. It's going to have to make a whole tree of 2 to the K samples fight pairwise. And what you can show is that there's going to be some hypothesis which is output with probability something like 2 to the minus K. So at the end of the day, if I can advance this slide. We can get a final algorithm by, again, just guessing a random case from among these D+1 cases, running the appropriate pairwise contests as necessary. And that what we get is, sorry about this, there exists some H such that the probability of outputting H is at least something like 2 to the minus D. Okay.
Mark, there's a question asking, what if the adversary does not try to maximize your error and instead tries to maximize the running time of the algorithm in the term of number of rounds?
Yeah, so this is a pretty bad algorithm in terms of computational complexity. Still, in any case, the number of fresh samples that the algorithm needs is going to be something like 2 to the D. And the running time is a disaster, something like 2 to the D times, all of these things that that the learner is going to have to do to, identify points on which the hypotheses disagree and stuff. So the point is, whatever horrible adversarial strategy is being executed in labeling your samples, you're still, after some horrible exponential time, at least 2 to the minus O of D likely to produce some hypothesis. Did that answer the question?
Yes.
Running time is not good.
Sure. By the way, Mark, don't feel a need to rush if you're especially in a rush. I mean, it's around 2 o'clock, but if you have more to say, that's fine. Just don't go on for another hour.
Okay. So I mean, I'm happy to talk about as much of Lemma 2 as people are willing to tolerate. So that was everything I had to say about Lemma 1. Any questions about anything? People, I guess since it's 2, people should of course feel free to leave.
Ambudge is interested in Lemma 2, for the record.
Okay.
As am I.
All right, so let's take a look at Lemma 2 now. So again, what we did in Lemma 1 is we showed that associated to any finite Littlestone, any class of finite Littlestone dimension, there's a globally stable pack learner. And again, the goal of Lemma 2 is to generically convert any globally stable pack learner into a differentially private one. Okay, so here's a somewhat more precise statement of what we do in Lemma 2. So we have some globally stable pack learner G, which uses M samples. And let's say that the global stability parameter is sigma. So associated to every distribution and every target concept, there's going to be some hypothesis which the learner is going to output with probability at least sigma. Then the claim is that from such a learner, we can construct an epsilon delta differentially private learner using something like M over sigma samples. Okay, so if you remember from the previous slide, M was something like 2 to the D, sigma was something like 2 to the D. So put together, this is something like 2 to the D. Okay, so let me give you, again, the proof idea for how we do this conversion. And the proof idea will just be in pictures. So the buzzwords associated to the pictures for those who are experts in differentially private algorithms are subsample and aggregate and private heavy hitters. You just like put those together in a reasonable way, you get this lemma. So here's what we're gonna do. So we have at our disposal this globally stable learner G. And what we're gonna do is we're going to run it on batches of independent samples, S1 through SK. Okay, so each S1 through SK is going to have size M and be an IID draw from the distribution D. Okay, so we're going to pass each of these samples into the globally stable learner, producing a sequence of hypotheses H1 through HK. Okay, and what we're gonna do is we're gonna pass these, this list of hypotheses into a differentially private heavy hitter identifier. So this heavy hitter identifier is going to look for hypotheses that appear frequently in this table, okay? And then spit those hypotheses out. All right, and now that we have what's hopefully a short list of hypotheses, it's going to turn out to be something like 10 over sigma of them. We're going to run the generic differentially private learner using this as our new concept class. Okay, so you can think of this as some kind of like hypothesis class reduction routine. We're going to produce a small list of candidate hypotheses. We're going to use the generic differentially private learner to select from one of these hypotheses using an additional fresh sample S prime. Okay, so what's the idea for why this algorithm works? So over here on the left, if I have a globally stable pack learner, then what I'm going to guarantee is that a lot of these hypotheses H1 through HK are going to be equal to this good hypothesis H. So H is going to be a heavy hitter with respect to this table H1 through HK. So the DP heavy hitter identifier is going to output a short list F1 through F10 over sigma that contains H. Okay, so we know that G is a pack learner and H, I didn't state it here, this was one of the issues that I was sweeping under the rug, but H is going to be doing a good job of labeling the sample. Okay, so there's going to be at least some hypothesis in this list F1 through F10 over sigma, which is good at labeling the sample. So the generic DP learner is going to find some hypothesis, which is good at labeling this fresh sample S prime. And this H star that it produces is going to be doing a good job of labeling with respect to the distribution. Okay, so any questions about the idea? Okay. So I just wanted to spend a few words describing this heavy hitter identifier subroutine in a bit more detail. So by now, this is a reasonably standard primitive in the design of differentially private algorithms. So what this heavy hitter identifier does is it, say it takes in as a parameter gamma bigger than 0. And the heavy hitter identifier takes as input a list of k things from some universe, U. In our case, U is going to be the space of possible hypotheses that the globally stable learner produce. And it's going to output a short list from the same universe. So the properties that we want from this thing are that first off, it's epsilon delta differentially private. Not going to be very useful if it's not. For every hypothesis, which is indeed a heavy hitter, so every H that appears at least gamma k times in the input, so a gamma fraction of times in the input, that's going to appear in the output list. The list is not going to have any false positives. So there aren't going to be any H's appearing in the output list. They appear fewer than gamma k over 2 times. That's going to guarantee, in particular, that the size of the list is small, at most 2 over gamma. And finally, this algorithm should work, let's say with high probability, as long as the number of inputs is reasonably small, at most log 1 over delta over epsilon times gamma. And the point I want to make about this sample complexity for the heavy hitter identifier is that this is something independent of the universe U. Okay, so the hypotheses in our setting could be arbitrarily complex things from some, infinite space. But the point is that this algorithm is not going to have any explicit dependence on U, or any dependence on what U was at all. And this sort of, in my experience, captures some of the magic of epsilon delta differential privacy, is that you can do this in the first place, that you can get sample complexity independent of the domain size for the heavy hitters identification problem. And one way that I like to interpret this result is as a statement that, at least in the context of private learning, when you don't care about concrete sample complexity and just want to separate finite from infinite learnability, this is kind of the only technique, right? It's like a reduction from, all learning settings to just this heavy hitters problem. Okay, any questions about this?
There's a question from Thomas asking, so is the assumption that the likely hypothesis H is also a good labeling?
Yeah, that's an assumption that I didn't talk about.
So he's asking, is that part of the proof of lemma 1 or part of the proof of lemma 2?
It's part of the proof of lemma 1.
So it holds in lemma 1, and then as you take it for granted and for when proving lemma 2.
Yep, that's right. Cool. So this is, again, one of the issues that I swept under the rug when describing lemma 1, and that, again, makes the proof more complicated.
So Marek, I have a question. This is Adam speaking.
Yeah.
Why do you need the generic DP learner step, the pink box on the right? So it seems like if you boost the error probability of the PAC learner sufficiently, then shouldn't it be that essentially everything coming out of each of the subsamples, like all the things that come out of the subsamples, are good? You just have to find one?
So we are indeed in a setting where everything coming out of the sample is good, but you have to identify a canonical one. So sort of the issue I have in mind is you might have two hypotheses that are both really good at labeling the data, but they're distinct. So they disagree on some point, which is irrelevant to the distribution.
Okay. I guess what I'm saying, if all of the H's on the left-hand side are good for the distribution, then your heavy hitter identification will find some of them, 10 over sigma of them at most. And you could just output any of those, right? Like any one of them. The heavy hitter just helps you find the name of one of them.
I see. Yeah. Yeah, that probably would work. We didn't think about the details of the particular algorithm that you described, but I don't see a concrete obstacle to just doing it that way. Okay, so yeah, you're suggesting still do the differentially private heavy hitter identification.
So if the algorithm G only outputs a good hypothesis with probability 90%, then you have to be careful, because all of the H, it could be that a bunch of the H's are horrible, and then you're in trouble. Then you want to do this extra step, right? And I was just wondering if an alternative structure would be just to boost in the sense amplify by using the usual tricks. using the usual amplification of the error parameter of a pack learning algorithm.
Yeah,
Like
that makes sense.
Inside of G, right? But maybe for sample complexity, this is even better. I don't know. It just seemed like you'd have one less.
I don't know. So yeah, this is just there are likely several possible ways one could do this. There's like essentially no impact to sample complexity by doing it in the particular way that we described. And it's also not clear to me like whether so it was just like one thing that we could do that was reasonably easy to write up.
Right. Okay. Right. Yep. Thanks.
But yeah, again, from like the 15 seconds of thinking about it, I don't see anything wrong with the suggestion that you made.
Either way, Lemma 1 is doing all the hard work.
Yeah, right? Exactly. Yeah. So really, like the only thing going on in Lemma 2 is the heavy hitter identification. The rest of it is sort of details. Anything else?
Actually, yeah, there's 2 more questions. One from Thomas asking how hard it might be to improve this result from exponential to say polynomial in D.
That's a good question that I can't really assess. So this so the exponential dependence is coming in Lemma 1. And we didn't really see any good avenues for getting rid of this like recursive tournament structure, making hypotheses fight in every step of the recursion, which like naturally leads to this exponential blow up. Yeah, I don't see a particular path to reducing the dependence to polynomial, at least if one thinks about doing the reduction in that way.
Sure. There's another question. I'm not sure I fully understand it, but it's asking, do you need the definition of differential privacy to hold for aggregated results?
So what's going on here, I guess, is so this differentially private heavy hitter identifier, you want this algorithm, or at least like this part of the algorithm, sorry. This part of the algorithm to be end-to-end differentially private. So what's going on here is that the DP heavy hitter identifier is differentially private with respect to changing one of the HIs. Okay, so this automatically gives you something that's end-to-end differentially private, because if I change one sample, so one Sij, then I change at most one of the HIs, which is going to change at most one of the inputs to the DP heavy hitter identifier, so I get similar probability distributions. That's the subsample and aggregate technique. Did that answer the question?
Indeterminate. There's no response.
Okay.
Let's assume so.
Can feel free to flag me afterward if you want further clarification. Okay, so again, that's the entire idea. One could do a sample complexity analysis for this thing. It's not terribly interesting. You need some number of samples in order to guarantee that the frequent hypothesis from Lemma 1 is likely to appear in the table, and that the heavy hitter identifier is going to do a good job of spitting it out to its output. You need some lower order term number of samples in order to run the generic DP learner to find H star. So you can add these things up. The total number of samples that you need is k times m, where m is the number of samples that go into each of the SI, plus this lower order term. And what you get at the end of the day is m log 1 over delta over epsilon times sigma. Okay, so I'm going to wrap up with what I think are some of the most interesting open questions that this line of work raises. Really, again, I think of this as, you know, a first step to understanding the sample complexity of private learning generically in more detail. So again, you know, our main result was showing that a concept class is differentially private learnable if and only if it has finite Littlestone dimension. Some concrete questions. Can we tighten the upper bound? Again, I said the best one can hope for this upper bound based on Littlestone dimension is something like order D. But, you know, a more ambitious goal from that would be to come up with some, you know, possibly different, like possibly extremely different combinatorial parameter associated to a class, which is able to characterize the sample complexity up to polynomial or even constant factors. So another question which sort of came up in the discussion is whether we could make our learning algorithm proper. So again, there are a couple of places within the learning algorithm. In particular, the use of the SOA immediately takes us out of proper territory. So whether we could get a proper learner, a proper private learner for all Littlestone classes, so a differentially private PAC learner, which is always guaranteed to output a hypothesis from the true underlying concept class. And this would have some interesting implications. So in particular, it would show that finite Littlestone dimension of a class implies the existence of a differentially private query release algorithm, and equivalently a synthetic data generating algorithm for that class. So another question that this raises is as follows. So one consequence of this work is that it bears on this irritating question about the parameters in differential privacy. So, you know, a natural question one can ask is that if I have, say, a differentially private learner with some sample complexity for, you know, epsilon being 0.01 and delta being most permissive, 1/10n, can I automatically convert that into a differentially private algorithm with much better parameters? Say, you know, epsilon being 1/1000 and delta being negligible in n. So we know how to do this for epsilon, but we don't really have a good way of doing this for delta. Now our result, you know, characterizing private learning in terms of Littlestone dimension shows, you know, implicitly this is possible. So if I have a 0.1, 1/10n differentially private learner, then that means that my class is finite Littlestone dimension, which means I can plug it into this, you know, this whole thing and get a learner with, you know, negligible delta. But it'd be really interesting to turn this into something like algorithmic and actually usable. The last question is whether we can find further applications of this new notion of global stability. Perhaps perform a more systematic study. So this notion of global stability seems to be related to some other notions of stability which have been shown to be useful for generalization. In particular, it seems to be related to a notion studied by Thomas and Lydia and their work on conditional mutual information. Okay, so sorry again for going over time, but thanks for listening and thanks for the questions and comments.
Awesome. Thanks so much for an excellent talk, Mark. People were really excited and interested. Yeah, let's open it up for, there were a ton of questions, but let's see if there's any more questions.
So do you think that this route of going via global stability is sort of the right way to get to, you know, poly D rather than 2 to the D? Or do you think it's possible to get a poly D lemma 1, or would the entire proof structure have to change?
That's a great question. So I think it's quite conceivable that both would need to change. One reason for this is that, like, really nothing is going on in lemma 2. We're just doing heavy hitters. And, you know, for concrete classes that people care about, like thresholds, for instance, like the way that you get these log star D kinds of algorithms for thresholds is most definitely not by doing some non-private thing and reducing to heavy hitters. There are like much more specialized techniques for adapting to the structure. So I agree that it's entirely possible that like a much more promising avenue to getting down to D or poly D would be to change both parts.
I mean, this is the sort of thing we should be able to prove a negative result for potentially, right? Like maybe we can go with,
yeah, like a lower bound for global stability.
All right, are there any other questions?
Does Zach have a question?
I think that was Teddy, perhaps, with a question.
Yeah.
So I have a question.
Yeah.
So thank you for the talk. It was really great. So there is this, so in the learning community, when we usually receive samples, it's like a noisy version of a concept class. Like in the linear regression, we see a linear function plus some Gaussian whatever noise, right? But it feels like the online learner essentially here breaks because you can never guarantee like maximum number of mistakes, right? So I'm wondering, do you think your results could be generalized to noisy, like learning via noisy example?
Yeah, so thanks a lot for this question. So there are two things I want to say about this. So first, I only talked about the realizable setting for our results, but it turns out that there's a generic conversion one can apply to differentially private PAC learners in the realizable setting to differentially private learners in the agnostic setting. In particular, the agnostic setting will handle noise tolerance as you described. So this characterization actually shows that the sample complexity of agnostically learning a class is also at most exponential in the Littlestone dimension. Another reasonable, so this is a generic conversion for all differentially private PAC learners. It turns out that there are analogs of agnostic learners in the online setting. One can combine the mistake-bounded learner with the SOA with some tricks using like multiplicative weights and stuff to get an agnostic learner in the online setting. We tried, but we didn't like really get anywhere with trying to use the agnostic online learner directly to get like an agnostic private learner. But carrying that out could also be an interesting direction.
Thank you.
Cool. Are there any other questions? Okay, I think we might have exhausted all the public questions, so I'm going to take us offline and then you can chat a bit more with Mark if he has time and you want to casually chat. Let me remind you that next week we'll have Rahul Ilango. 2 weeks from now we'll have Mike Kim, and the week after that we'll have Cliff Stein speaking. So thanks a lot for joining, everyone.
Thanks, everyone.